Hello trigonometry students, my name is Emigh, and this video is our discussion on Chapter 6, Inverse Circular Functions and Trigonometric Equations. To be a function, the graph must pass the vertical line test. Here we have a graph of sine of x, and we're being asked, is this a graph of a function? Well, it needs to pass the vertical line test if it is, and that would be any vertical line that we draw would intercept the graph once, exactly once, okay? And so just testing a few vertical lines, they all intercept this graph once, and then thinking about this graph as it continues on to positive infinity and in this direction to negative infinity, this periodic function, any vertical line that we would draw would cross that graph exactly one time. So our answer to, is this a graph of a function, is yes, because it passes the vertical line test. To be a one-to-one function, the graph must pass the vertical and the horizontal line test. So using the same graph, let's check, is it a one-to-one function? Well, we already know that it passes the vertical line test, and we're told that it also has to pass the horizontal line test. Same requirements for the horizontal line test. Any horizontal line that you draw must intercept the graph exactly once. Well, I've got a counterexample right here. This graph, this line that I'm drawing, this horizontal line, touches our function there, again there, same line, again there, and it would actually continue to intercept with this, the graph of sine of x infinitely many times. So the answer to the question, is it a one-to-one function, is no. Because as soon as you can draw a horizontal line that intercepts the function more than once, it is not a one-to-one function. Now we're asked, can we cut out part of the graph that is one-to-one? So think about maybe having a snippet tool. Is there any part of this graph that you can cut out that would pass the vertical and the horizontal line test, making it one-to-one? The answer is yes. Here is one example right here. If we cut this piece of the graph out, this piece of the sine function is not only a function because it passes the vertical line test, but it's also a one-to-one function because it passes the horizontal line test as well. You can see that all the vertical and horizontal lines that we could possibly draw would only intercept the function one time. What that means for us for Chapter 6 is that this part has an inverse. So sine of x, the entire thing does not have an inverse because it's not one-to-one, but this piece does. All right, let's check the same thing using the graph of cosine. Is this a graph of a function? If you said yes, nice work. Every vertical line we could draw would intercept the function or the graph one time, making it a function. Is it a one-to-one function? If you said no, you did that correct. That is correct. Drawing a horizontal line, we can see that it'll intercept the function more than once, so it is not a one-to-one function. Can we cut out part of it that is one-to-one? If you said yes, very nice. One example would be this part right here. This piece of our function, well, this piece of our graph is a function because it passes the vertical line test, and it is a one-to-one function because it passes the horizontal line test as well. As you can see, any vertical or horizontal line that we draw will intercept this piece of cosine of x one time, making it a one-to-one function. What that means for us for Chapter 6 is that this piece right here will have an inverse. All right, let's talk about what it means to have an inverse. Inverse functions. A function can only have an inverse where it is one-to-one. That is the point of the first slide. It's defined as the inverse of f is equivalent to the set of all coordinates y comma x such that x comma y belongs to f. The domain of f is the range of the inverse of f. The range of f is the domain of the inverse of f. Caution, the -1 that we see in the notation for the inverse function is not an exponent. So make sure not to accidentally make this move right here. Okay, these are not equivalent. Graphs of inverses are reflections in the line y equals x. Two graphs to look at here. This is just a point, okay? So it's reflection in the line y equals x. Here's the line y equals x. I like to think of this as the mirror, because that's where we often see a reflection. So if this point right here looked, so line of sight looks into the mirror, the reflection, would be on the opposite side of the mirror, the same distance away. Another way to elaborate that, let's pretend that this is the point 3, -1. Goodness. So if this is the point 3, -1 for our function, then the inverse of it would be the coordinate -1, 3. And that checks off definition right here. The domain of f is the range of its inverse, and the range of f is the domain of its inverse. You can see here the x and y's swap. Here we have a one-to-one function, and if we went point by point, graphing its reflection in the line y equals x, we would end up with this red dashed line, which is the inverse of the original. This point's interesting to think about. This point is actually on the mirror, I'm going to call it, the line of reflection. If you were to walk up to a mirror and put your finger on the mirror, your reflection would be touching your finger. So this point right here on the mirror, its reflection is also on the mirror, or on the line of y equals x. And you can see that each point is on the opposite side of the mirror, the same distance away from the line y equals x as the original function. Okay, let's go back to inverse sine, or another way to say it is arc sine. It can be written as y equals the inverse of sine of x, this notation here, or it can be written as y equals arc sine. They are equivalent. The graph of arc sine is the reflection in the line y equals x. I'm going to just draw the line y equals x. I don't want to clutter up this graph, but I do want you to know where it came from. So if this is the line y equals x, let me switch colors, that might be helpful. Okay, and the original function we've got here, I'm graphing that piece of the sine function that we determined to be 1-to-1. There we go. If you go back 2 slides, you can see it. This is the piece of the sine function that we determined to be 1-to-1, and therefore its inverse is the reflection in this mirror, or this line y equals x. So this graph that you guys are seeing is arc sine. All right, I'm going to erase my pen now because I don't want it to clutter this graph right here of the inverse of sine. Okay, domain for arc sine is -1 to +1. Range of arc sine, -π/2 to +π/2. And these points are included. Notice the brackets. This function, as we travel from left to right, is increasing the entire time. It is also continuous the entire time. That means that at no point in graphing this did we have to pick up our pen. Was there like an undefined, an open circle, or an asymptote? So it's increasing, and it is continuous on its domain from -1 to +1. And then this is a table of some of the most frequently used points for arcsine. And this table might look familiar to you. In fact, if you take these two columns and you switch them, it is the sine table that we've been working with all semester. So let's just look at one of these here. Let's look at this one. If on our x-axis we are at -1, so here, so starting at the origin, we go to -1, then arcsine has a value of, right here, -pi/2, which is this, that's in radians, same thing in degrees would be -90 degrees. All right, so we're going to be given exercises that ask us to find the value of y in equations that include arcsine or inverse sine. So let's work with this one here first to see what we're supposed to do. Y equals arcsine of 1/2. Well, if we were to just use the arcsine table, that's one strategy. Just use the arcsine table from the last slide. 1/2 right here. Or on the graph, if we were at 1/2, the value would be up here at pi/6. So here we are at 1/2. Here we are at pi/6 radians, which is equivalent to 30 degrees if you're working with degrees. So that's one way. If you have the arcsine table, just use it, and this y right here would be equal to pi/6 is equal to arcsine of 1/2. All right, let's say you do not have the arcsine table. Maybe it's a closed book assessment, or you just haven't committed that table to memory, but you have committed the sine table to memory. You can use that table as well. You just have to do a little bit of work first. So to use the sine table, we'll need to manipulate this equation to get rid of arcsine. We get rid of it by moving it to the other side of the equal sign, and when it moves to the other side of the equal sign, it will become sine. So it looks like this. Arcsine, we would use its inverse operation to move it to this side of the equal sign, and it becomes sine of y is equal to 1/2. Notice how the movement of arcsine looks when it passes to the other side of the equation, to the other side of the equal sign in the equation. Okay, so now we have sine of y is equal to 1/2, and if we use our table for sine, we want to look for the value of y. Now, careful, you can't use the entire table. We only want to look in the range -pi/2 to +pi/2, because that is where sine has an inverse. And we'll find that what value of y in that range does sine equal 1/2. So looking at the sine table, we would find that that is at pi/6. So either table can be used based on what resources you have available for you. Oftentimes people have only committed a small part of this original sine table to memory, and so anytime we can reference that part that we've committed to memory to get us through more exercises, then that one resource becomes more and more valuable to us each time. All right, let's try this one right here. Y equals inverse sine of -1. This could also be written arcsine, you guys. Just really want you to recognize that it's just a different notation, okay? All right, to use the arcsine table, we would find that arcsine of -1 is equal to -pi/2. That's just on our table from the last slide. Using the sine table, we would do the same thing we did over here. We would want to get rid of the inverse sine by using its inverse function, which is sine. That looks like moving it to the other side of the equal sign, where it will become sine. So we take this right here, we move it to the other side of the equal sign using its inverse operation, and now we have sine of y equals -1. So we can use our sine table and make sure you're only looking for values between -pi/2 and pi/2, where sine will be equal to 1, and we will find that that is at -pi/2. So two different uses of resources to get to our answer here. C, y equals inverse sine of -2. If we take sine inverse right here, inverse operation, moving it to the other side, now we're working with sine of y equals -2. That might be a quick red flag for you there. -2 is not in the domain of sine. Sine's domain is -1 to +1, and therefore sine inverse of -2 does not exist. And that's fine. There's nothing wrong with that. That's informative, and we would write D and E for y equals the inverse of sine of -2 does not exist. All right, let's talk about inverse sine or arc cosine, written as y equals inverse cosine of x or y equals arc cosine of x. This graph right here comes from the reflection in the line y equals x. You can refer back to the first slide in this video, and you'll see that this graph right here came from the piece that we cut out, the 1-to-1 piece of cosine. It was over here a little bit more. It was all in quadrants 1 and 4. And if you graph its reflection or mirror image in this line y equals x, that is where this graph came from. This is the graph of arc cosine. Its domain is -1 to +1. Its range is 0 to pi, including 0 and pi. This one is decreasing, and arc cosine is also continuous, so decreasing and continuous on its domain. Arc cosine table, that can be useful to us if we have this as a resource, some of the frequently used values. And similar exercises, y equals arc cosine of 1. We can use the arc cosine table from the last slide to find that that is equal to 0, or we can manipulate that equation, getting rid of arc cosine using its inverse operation, moving arc cosine to the other side of the equal sign would be cosine of y equals 1, and then using the cosine table, make sure you're only looking for the y values between 0 and pi, and we will find that that is equal to 0. All right, let's go again. Like this one here, trying to point out, make sure you know that arc cosine could have been used instead, different notation, but equivalent functions. We can use the arc cosine table to find that y equals the inverse function of cosine of negative radical 2 over 2 at 3 pi over 4. Or we can use the, or we can use the cosine table by manipulating our function, moving inverse cosine, using its inverse operation. When it comes to the other side of the equal sign, it will become cosine of y is equal to negative radical 2 over 2. Looking at the cosine table, make sure you're only looking for y values in the range 0 to pi, and you will find that that is equal to 3 pi over 4. One more down here, similar to this y equals inverse sine of -2, we're talking about y equals inverse cosine of -2, and if we move this inverse cosine using its inverse operation, we have cosine of y equals -2, which we know -2 is not in the domain. Domain of cosine is -1 to +1, and therefore inverse cosine of -2 does not exist. Nothing wrong with that. That's very informational. We just write D and E for y equals inverse cosine of -2 does not exist. Inverse tangent or arctangent, written y equals inverse tangent of x or y equals arctangent of x. The graph of arctangent, you're probably we're used to seeing arctangent increase like this, approaching vertical asymptotes, but we can see that arctangent actually has horizontal asymptotes in the same location at, well, corresponding location once you switch domain and range. So at pi over 2 and negative pi over 2, inverse tangent will approach those asymptotes. It crosses through the origin. Its domain is negative infinity to positive infinity. Its range is negative pi over 2 to pi over 2. Notice that we're using brackets here because it does not include negative pi over 2 or positive pi over 2. It is increasing as well as continuous on its domain. Noting that y equals plus or minus pi over 2, those lines would be representative of the horizontal asymptotes that we see here. And the arctangent table, some frequently referred to values given to us here. Okay, let's go to exercises using arctangent. Here we're asked to find sine of inverse tangent of negative radical 3 over 3. Let's take this entire thing. Wouldn't it be nice if it was just sine of theta, like this? Sine of theta. Then we could just use our table. We know how the graph of, or we could use the graph. We know what the sine function looks like and how it behaves. We could even use the unit circle. We've got so many tools if we're just talking sine of theta. But we don't have just sine of theta. We have sine of inverse tangent of negative radical 3 over 3. So what we're going to do is let theta be equal to everything we have here. And now we're going to work with just this right here, the inverse tangent of negative radical 3 over 3. If we refer to the arctangent table, we will find that our theta is equal to negative pi over 6. Now let's use that information, and if theta is negative pi over 6, we get to change this original expression into just sine of negative pi over 6. Doesn't that look so much nicer from here to here? And that's a strategy we use a lot, substitution like that. Let theta equal whatever you guys have here. Use your resources to figure out what theta is. And now we're working with sine of negative pi over 6, which is equal to negative 1/2. All right, I want you guys to try one. Find cosine of the inverse of tangent of 1. Go ahead and pause the video and try that one now. Welcome back. Let's see how you did. If you wrote something along the lines of let theta equal the inverse tangent of 1, and then came up with theta being equivalent to pi over 4, doing great, on the right track. Then take that, put it back into our expression, cosine of pi over 4, which we know has a value of radical 2 over 2, then you got it right. Nice work. Trigonometric equations. Let's look at an example. Here we're asked to solve 2 sine of theta plus 1 equals 0, and we're looking for all the solutions that exist on this interval from 0 to 360 degrees. Not including 360, that's why we have the parenthesis, including 0, that's why we have the bracket. All right, hopefully we can move this stuff around and just isolate theta and we'll be all good. So we take the positive 1, use its inverse operation, which is negative 1, move it to the other side. Okay, going well. Let's make another move. Let's get rid of this multiplied by 2. Use division, both sides of the equal sign. Now we're at sine of theta equals negative 1/2. This is going really well. And we know that when theta equals 210 degrees as well as 330 degrees, sine will have a value of negative 1/2. Notice that our solution set has 2 answers, and both of those answers are in the interval 0 to 360 degrees. That's because we were only asked to address sine of theta on the interval from 0 to 360, so one time around the unit circle, or one period of sine. Now, these directions are going to change on us a little bit. We're asked to solve the equation 2 sine of theta plus 1 equals 0, except this time we're asked to find all of the solutions. Well, we have 2 of them so far, so that's good, but there are many more. So what we're going to do is add integer multiples of the period of the sine function, which is 360 degrees, right? 0 to 360 degrees is what it takes to complete one period of sine. And we're going to add integer multiples of 360 degrees to each of our solutions in part A, okay? So at 210 degrees, we're going to add integer multiples of 360 degrees. And 330 degrees, we're going to add integer multiples of 360 degrees. Why? Well, we know that the sine function is a periodic function, so heading in the positive infinity direction or in the direction of negative infinity. We're going to keep hitting that value of -1/2 over and over every 360 degrees. Doesn't matter if we're adding or subtracting. Okay. It looks like this. 210 degrees plus 360 degrees times any integer n, as well as the set of all values 330 degrees plus 360 degrees times any integer n. Oh, and it's stated here, where n is any integer. So now we have a solution set that represents all solutions for this equation. So careful with your directions with these exercises. If it says over just a specific interval, then just give a solution set within that interval. But if it says for all solutions, then make sure to give a solution set representing all of the solutions. All right, next one, we're asked to solve sine of theta times tangent of theta is equal to sine of theta over the interval 0 to 360 degrees. All right, let's manipulate this equation by setting it equal to 0. So let's take this sine of theta, subtract it from both sides of the equal sign. Notice we're not just moving sine, so we're not introducing inverse sine, which we just spent a lot of time on inverse sine in this video. So I don't want you to think that we're doing the same thing here. Here we're moving the entire sine function with its angle theta. So to move the entire thing, we would use subtraction. If we were just moving the sine function, we would use inverse sine to move it. But moving the entire term, subtraction. All right, so now we have set this equal to 0. That can be useful to us because our two terms have a sine theta in common, so we factor out sine of theta, leaving us with tangent of theta minus 1 equals 0. Then we'll use the zero product property, which states that if you multiply two things together and get a value of 0 as your answer, one of those two things has to equal 0. So we either have this right here, sine of theta being equal to 0, or our tangent theta minus 1 must be equal to 0. Tangent theta minus 1 equals 0. Let's go ahead and move our minus 1 to the other side of the equal sign using addition. And sine of theta is equal to 0 at 0 degrees, also at 180 degrees. So this equation led us to these two. Or maybe this factor is equal to 0. Well, for that to be equal to 0, we would need tangent of theta to be equal to 1, and that occurs when theta equals 45 degrees or when theta equals 225 degrees. So this factor led us to these two. So we found 4 possible values for theta. They are all within our interval 0 to 360 degrees. All 4 of these would make sine of theta times tangent theta equal to sine of theta. Writing that up as a solution set, we list the 0, the 45, the 180, and the 225 degrees. In this next example, we're asked to solve cosine of 2x being equivalent to cosine of x over the interval 0 to 2 pi. Okay, just like the last couple, it would be really nice if we could just manipulate this equation and try to isolate cosine of x. But before we do that, it's not going to be quite as straightforward as just subtracting something from both sides of the equal sign or dividing both sides of the equal sign by something. We need to focus on this right here, cosine of 2x. This is one of our double angle identities that we've talked about, and we know that cosine of 2x has three equivalent forms. We've got cosine squared of x minus sine squared of x. It's also equivalent to 1 minus 2 sine squared x. And it's also equivalent to 2 cosine squared x minus 1. So we could take this cosine of 2x and we could replace it with any of these 1, 2, or 3 equivalent forms from our double angle identities. Now, there's no wrong choice, but there is certainly an easier choice. So strategically, we only have cosine in this equation, so we wouldn't want to, ideally, we wouldn't want to introduce sine into our equation. This first one here has sine in it, so I'm going to avoid that one. This one here has sine, so I'm going to avoid that one. So I'm going to go with this third one here, making our equation twice cosine squared of x minus 1 equal to cosine of x. That was just substitution using a double angle identity. Okay, now this we can set equal to 0. Doing so puts it into a trinomial that can be factored into 2 cosine x plus 1 times cosine x minus 1. If you're not quite sure how we got from this step to this step, I would suggest you go off to the side and do a little factoring review. Okay, I want you guys to try and factor 2x squared. All I'm doing is turning this trinomial, I'm taking cosine out of it and I'm changing it just to an x. So then there's a minus sign. I'm taking cosine out, then there's a minus sign, then there's a 1, then there's an equal 0. All right, so if you were being asked to factor this trinomial, we would factor into 2 binomials. And those 2 binomials would be 2x and 1x. We need to make our last terms multiply to -1. We would need a positive 1 right here and a negative 1 right here. This is the factored form of this trinomial. To check your work, anytime you factor, if you want to check your work, you can use the distributive property. So multiply, that gives us 2x squared, multiply, negative 2x, multiply, it's positive 1x, and multiply. That's negative 1. Combine like terms right here in the middle, and that gets us right back to our original trinomial. So our factored form and our original trinomial are equivalent, so we know we factored correctly. All right, that skill right there is exactly what we did right here. See the answer in the factored form? It's 2x plus 1, x minus 1. Putting cosine back in for x, we have 2 cosine of x plus 1 times cosine of x minus 1. That's how we got from here to here. All right, now applying the zero product property, one of those 2 factors must be equal to 0. The first factor is equal to 0 when cosine of x is equal to -1/2. That occurs at 2 pi over 3 and 4 pi over 3. Our second factor is equivalent to 0 when cosine of x is equivalent to 1. and that occurs when x equals 0. Making our solution set, making the solution set 0 radians, 2 pi over 3 radians, 4 pi over 3 radians, all within this interval, and those are the three solutions that would make cosine of 2x equivalent to cosine of 1x. All right, I'd like you to try this example. Solve cosine of 2x equals 0 over the interval 0 to 2 pi. To get you started, I want you to notice that this right here has a double angle identity. Oops. It's on the last slide, so use substitution to get rid of this, and pause the video and try that now. Welcome back. If you use the double angle identity, cosine of 2x equals 2 cosine squared x minus 1, you're on the right track. That would make our equation look like this. Twice cosine squared x minus 1 equals 0, and that just came from here. Add 1 to both sides of the equal sign. Divide both sides of the equal sign by 2. Take the square root of both sides of the equal sign. Recall that if we introduce a square root into an equation, we need to address the positive and the negative root. The square root of 1/2 after rationalizing the denominator is radical 2 over 2. Let's continue our work up here. Cosine of x is equal to the positive root, radical 2 over 2, at pi over 4 and 7 pi over 4. Cosine of x is equal to the negative root, radical 2 over 2, at 3 pi over 4 and 5 pi over 4. If you want to sketch a little graph of cosine, that can help show that why we're getting 4 answers. Cosine of x will hit this value of radical 2 over 2. It's going to hit the positive one there, and then the negative radical 2 over 2, it'll hit there, there, and then the positive radical 2 over 2 again right here. Let me just label that so you can see it. And this one is the negative radical 2 over 2. So the positive root, radical 2 over 2, that occurs at pi over 4, and again at 7 pi over 4. That's where those two answers came from, or you may just be referring to the table, which is fine. And then the other two answers are here. This is 3 pi over 4, and here again at 5 pi over 4. So just in this interval from 0 to 2 pi radians, cosine of x takes on the value positive or negative radical 2 over 2 4 different times. Writing that as a solution set, we have pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. All right, that will finish our discussion on chapter 6. So please go to your chapter 6 homework and do those exercises now. My name is Jami Emigh. Thank you for being here, and I will see you next time.